Astronomers have achieved a major and unprecedented feat. They have refined the orbit of 3I Atlas, only the third confirmed interstellar object, using spacecraft orbiting Mars. By combining these Mars-based observations with Earth-based data, scientists have improved the accuracy of the comet's trajectory by percentage missing from original text, almost 10 times. The Atlas has discovered the most precise path ever calculated for an interstellar visitor. This breakthrough not only clarifies where 3I Atlas came from and where it's going, but also demonstrates a new method for tracking objects passing through our solar system. In this video, we'll explain what was discovered, why it matters, and what's next. Let's get started. Comet 3I Atlas was first detected in July 1, 2025. According to the Atlas survey in Chile, within hours of its appearance, astronomers realized that its movement did not correspond to that of typical solar system comets. Its trajectory was hyperbolic, indicating that it was not bound to the Sun and would pass through our system only once. This immediately placed it in the rare category of interstellar visitors, following Oumuamua and Borisov. Early observations relied on ground-based telescopes, which tracked the object as it approached the inner region of the solar system. But interstellar objects are difficult to characterize from Earth alone. They move quickly, spend little time at favorable angles, and small measurement uncertainties can rapidly widen. Although numerous observations were collected in the early stages, astronomers still struggled to determine the comet's exact path with the necessary precision. A unique opportunity arose in early October 2025 when 3I Atlas became approximately 29 million kilometers from Mars. The geometry between the comet, Mars, and Earth aligned in a way that made additional observations possible from a completely different vantage point. The Trace Gas Orbiter of ESA's ExoMars mission and the Mars Express spacecraft, both orbiting Mars, attempted to capture the comet using cameras designed for high-resolution images of the Martian surface, not for faint objects tens of millions of kilometers away. Capturing images of 3I Atlas from Mars orbit required compensation for the high speeds of the spacecraft, approximately 14,000 kilometers per hour, and for the comet's low brightness. The resulting images weren't visually impressive, but they were scientifically essential. The spacecraft's positions are known with far greater precision than ground-based telescopes can easily achieve. This made the images valuable for triangulation, allowing scientists to create a geometric baseline between Earth, Mars, and the comet. When analysts combined these Mars-based measurements with terrestrial data, the trajectory solution improved by almost a factor of 10. This was the first time a spacecraft orbiting another planet was used to help calculate the orbit of an interstellar object. The refined trajectory shows that 3I Atlas reached perihelion on October 30th and will make its closest approach to Earth on December 19th at a safe distance of 270 million kilometers. The improved orbit also allows telescopes to continue tracking the comet with greater precision as it weakens while exiting the solar system at almost 250,000 kilometers per hour. Beyond the discovery, this event demonstrated a new approach to tracking fast-moving, distant objects, an approach that may become increasingly important with future interstellar detections. Comet 3I Atlas is scientifically fascinating, not only for its interstellar origin, but also for its unusual composition and behavior. Spectroscopic observations from several observatories indicate that its coma is dominated by carbon dioxide, with water vapor and carbon monoxide also present. Most comets in the solar system switch to water-driven activity when heated by the sun, but 3I Atlas's strong carbon dioxide signature suggests that it formed in a much cooler region of its original system, where carbon dioxide ice was more abundant. This volatile profile indicates a different chemical environment around its parent star. The high ratio of carbon dioxide to water likely reflects conditions that do not commonly occur in the part of the solar system where typical comets formed. It also points to how planetary systems can vary widely in the types of icy bodies they produce. Polarimetry, the study of how light is scattered by dust particles, provides further insights. The measurements reveal a deeper negative polarization branch than is normally seen in solar system comets. This likely results from differences in the texture or structure of the dust grains, possibly caused by prolonged exposure to cosmic rays over millions of years spent between star systems. Dust grains traveling through interstellar space are continually altered by radiation, gradually reshaping their optical properties. Together, these findings suggest that 3I Atlas differs significantly from both Oumuamua and Borisov. Oumuamua did not exhibit clear cometary activity, while Borisov resembled comets in our system, but with some distinct traits. 3I Atlas falls between these cases, clearly a comet, but chemically and physically distinct from objects formed near our Sun. The trajectory enhanced by Mars-assisted triangulation also allows researchers to test for non-gravitational accelerations, such as slight impulses caused by asymmetric outgassing. Detecting these effects helps scientists understand the level of activity, mass, and internal structure of the core. Precise measurements from multiple observation points make it easier to detect small variations that would be missed in less precise orbital calculations. Scientists also observed that 3I Atlas brightened and shifted to a bluish hue after emerging from behind the Sun. This may reflect a change in dust or gas production as surface layers heat up and release fresh material. These variations provide further clues about its composition and the physics governing its behavior. By studying 3I Atlas, researchers gain another data point in the growing catalogue of interstellar material, strengthening theories about how other planetary systems form and what types of objects they eject into interstellar space. Music, music, music. The successful use of spacecraft orbiting Mars to refine the trajectory of 3I Atlas marks a turning point in how scientists track objects entering the solar system. Until now, orbital calculations relied almost entirely on observations made from Earth. This event shows that spacecraft on other planets can significantly improve accuracy, especially for faint, fast-moving or poorly positioned objects from an Earth-based perspective. This has clear implications for planetary defense. If an asteroid were to approach Earth from a direction difficult to observe with ground-based telescopes, such as from near the Sun, data from orbiters around Mars or Venus could provide essential measurements. As more spacecraft operate around multiple planets, the solar system increasingly functions as a distributed observation network, rather than a single planet-based viewpoint. The 3I Atlas campaign also highlights why missions designed for rapid reaction are becoming important. ESA's Comet interceptor, scheduled for launch in 2029, was designed to wait in space until a suitable target appears. Its design is intentionally flexible, making it capable of intercepting a dynamically new comet or potentially another interstellar object. If such a mission were already operational, it might have been possible to obtain short-range data on 3I Atlas. At the same time, ESA's JUICE spacecraft is currently collecting additional observations of 3I Atlas as it travels towards the Jovian system. Although this data will be processed later, it represents another observation point, reinforcing the value of observations from multiple locations. These developments support growing discussions about establishing interstellar rapid response missions, either with spacecraft stationed in heliocentric orbit or with multi-stage vehicles designed to be launched at short notice when a new interstellar object appears. Since such objects are rare and move rapidly, the ability to deploy a spacecraft quickly may be the only way to obtain direct, close-up measurements in the future. From a scientific standpoint, Each interstellar object expands our understanding of how planetary systems form. Differences in volatile content, dust composition, and activity patterns help identify which characteristics are common among star systems and which depend on local environments. With its unusually high carbon dioxide content and distinct dust properties, 3i Atlas provides a valuable benchmark for these comparisons. The refined trajectory will allow researchers to continue observing the comet during its December passage, collecting the last high-quality data before it becomes too faint to study. After that, it will continue on its hyperbolic path, leaving the solar system and returning to deep interstellar space. Events like this demonstrate that as our observation networks expand, our ability to track and understand interstellar visitors will improve, laying the groundwork for deeper exploration of extrasolar material in the coming decades. 3i Atlas gave us a rare glimpse of material from another star system. Using Mars orbiters to track it has propelled interstellar science forward. Each visitor enhances our understanding of how planetary systems form,